All right, guys. So we'll pick up right where we left off. And what we're going to be doing is looking at some math, okay? Just like we did in the previous lecture. We can, or not the last lecture, but the one before that, we can set up Rice tables for the acid equilibriums because we're dealing with the same thing. We have a Ka, we call it a Ka because it's an acid dissociation constant. So we have a Ka, it's products over reactants just like it always has been. And we can set that up and use these tables to help us determine what those concentrations are. So in this example that I have right here, I have HF going to H plus and F minus. Okay? Ka equals H plus times F minus over HF. And that has a value of 7.1 times 10 to the minus fourth. That's actually in the exam handouts. That Ka is equal to X times X, so H plus times F minus, over the concentration of HF. That's how we look at this, all right? No matter what we start with, remember that we've made some assumptions about how these things work. And so we've assumed that whatever our initial concentration is, it's huge compared to that X. Okay, so we'll always get rid of that X portion when we do this. And therefore, we'll end up with X squared is equal to the initial concentration times the K. And then we'll take the square root of that to figure out what the X is. And then X represents not only the H plus, but also the anion, here the F minus. Okay, so that's how we're going to do that. Now, does it happen that you might someday need the quadratic to be able to do this? Yes. Now, am I going to ask you to do that? No, I will never ask you to do that. But what I wanted to show you here is that you may see this. And so when that happens, we don't make the assumption that X is small. We end up having this X squared and an X here, so we've got to use the quadratic to solve for X. When we do that, we see that it's 1.85 times 10 to the minus 2. And that's very, very, very close to the 0.019 that we already calculated. We can calculate what percentage that number is of the starting. Okay, so if I calculate the percentage of the 0.5, I put the 1.85 times 10 to the minus 2 divided by the 0.5 times 100. That's less than 5%. If it's less than 5%, we consider that a valid choice to ignore it. Okay, so that's what you guys are always going to do. Whether it's a valid choice or not, that's what you will do. Right? But you may see this out in the universe, and that is what this is representing. Okay, that would give us an exact value for this. And we can, when those numbers are very close to each other, then we need to work with that. Okay, so that's our Rice table for an acid equilibrium. It's set up exactly the same as what we did before. We have our initial condition of 0.5 molar acid that's put in there. No H plus, no F minus. Our change is negative X for the HF. That gives us an H plus and an F minus. So that's, both of those are plus. Our equilibrium is going to be the 0.50 minus X. And then X and X, we ignore that X. And that's how we get this math that we did over here. Okay, so that's what that setup looks like. And now that I've shown you what the setup looks like, let's try a couple together. So I'm going to do a couple with you here, and then there are going to be some that are going to get done, and I'll put the answers on D2L. All right, they're later on in this lecture. Okay, but that's the way we're going to handle this. So when we talk about Rice for weak acids, we're talking about acetic acid, CH3COOH, has a Ka. So I know that this is going to be a dissociation. I know that I'm going to end up with an H plus and CH3COO minus, so all that other stuff that's left, that has a Ka equal to 1.8 times 10 to the minus fifth. Okay. What is the pH of the solution of acetic acid? That is 5.46 times 10 to the minus fourth mole. So I have some initial conditions. I know that this is 5.46 times 10 to the minus fourth. We assume that H is 0. We assume that the acetate ion is 0. Our change is going to be a negative X for the acetic acid, a plus X for the H, and a plus X for the anion, so the acetate ion. That means that this equilibrium is going to be 5.46 times 10 to the minus fourth. And of course, that's the minus X, but we ignore the minus X, so I cross it out. This is going to be an X, and this is going to be an x. And that means that my Ka is equal to H plus times the CH3COO minus divided by the CH3COOH. That's equal to x times x over 5.46 times 10 to the minus 4th. Okay. I also know that's equal to the 1.8 times 10 to the minus 5th. So my x squared is equal to 1.8 times 10 to the minus 5th times 5.46 times 10 to the minus 4th. So if I do some happy math with that, I find that 1.8 times 10 to the minus 5th times 5.46 times 10 to the minus 4th gives me x squared equal to 9.828 times 10 to the minus 9th. And if I take the square root of that, I get an x equal to 9.91 times 10 to the minus 5th. And of course, I reported it as 3 sig figs because the original concentration I got was 3 sig figs. I did not base that off of the Ka because we typically only ever see Kas with 2 sig figs. Okay, so it's going to be based on the initial concentration I had. If that's the case, and I got asked what the pH was, because that's what they wanted to know, I know that the pH is equal to the negative log of the 9.91 times 10 to the minus 5th that I just calculated. And that is going to give me negative log second answer, 4.0. 4.00. Yay, awesome. I did it. Go me. That's fabulous. All right. So that's what that's going to look like. Okay. When we do this for a second acid, acetylsalicylic acid, okay, is C9H8O6. Has a Ka equal to 3.0 times 10 to the minus 4th. Okay. Now, this is an acid. It says that it's an acid. So this is my R, this is my I, this is my C, this is my E. So I know that this is going to decompose. It's going to give me an H plus, and then I'm going to be left with anything else that's left. So C9H7O6 minus. That's what's left. I know that initially I have, was the pH of a solution, and I want to know pH. That is 6.38 times 10 to the minus 5th. 6.38 times 10 to the minus 5th. Okay. I don't have any of the H plus, I don't have any of that anion. I know that my change is negative x there, plus x here, plus x here. My C9H8 is going to be the 6.38 times 10 to the minus 5th, minus x, but we ignore the x. My H plus is going to be x. My C9H7O6 minus is going to be x. And so I know that my Ka, which is equal to the 3.0 times 10 to the minus 4th, is equal to the concentration of H plus times the concentration of C9H7O6 minus over the concentration of C9H8O6. And I can plug in for that. So 3.0 times 10 to the minus 4th is equal to x times x over the 6.38 times 10 to the minus 5th. X squared is then equal to 3.0 times 10 to the minus 4th. 3.0 times 10 to the minus 4th times 6.38 times 10 to the negative 5th. Or 1.91 times 10 to the minus 8th. Take the square root of that. That gives me an x equal to 1.38 times 10 to the minus 4th, since that's my x, which is also the H plus concentration, my pH equals the negative log of the 1.38 times 10 to the minus fourth, and that's equal to 3.85, 3.86. Okay, getting 3 sig figs because 3.859. Sorry, it should be 3 sig figs. And since it's 3 sig figs, I need 3 decimal places. Don't forget about that. Okay. Now, does it seem like I'm doing that very, very quickly and knowing exactly what to do and just holding my calculator and doing that next thing? Yeah, it does. And that's because I've done this 8 million times. Practice will get you there. All right. It's not necessary to do it that fast. It is necessary to know how to do it. One of the things that I've found is that working with the acids and the bases, the weak acids and bases, makes it easier to work with the equilibrium constant tables, because those are actually more complicated most of the time because you have 2s and 3s and 4s, all over the place. This tends to be just acid goes to H plus anion. And so the math and the setup is much easier. And so the familiarity working with these, even though they're easier, will help you with working with the ones from the chemical equilibrium. So that's the hope. So we don't need to use the quadratic. You can always use the assumption that x is small, and that will get you the values that you need to be able to do that. Okay? Questions, comments, problems on how we set any of that up. Now, I did say that there will be more answers on D2L, there will be more practice on D2L, there will be practice in ALEKS, there will be plenty of practice for you. I think that it should be enough to get you where you need to be, but if it's not, talk to me about it. I'm more than happy to walk you through any of it because I know that I can do it pretty fast. I'm hoping that the ability to stop and pause and go back will be able to help with that, but I also know that it's going to require you putting your hands down, writing these things out, and doing some of this practice on your own to be able to do this, okay? Practice, practice, practice. I know it sucks, but that's what's going to get that through your head. So I hope that helps. I'm going to stop sharing now.